Okay. In our previous classes, the previous class we completed the basic part related with the Boolean algebra, in particular various operators, or operator, and operator, not operator, and we listed few of the properties on these operators as the Boolean algebra properties. Related to the Boolean algebra properties, we discuss few of the questions. Few of the questions are maybe few questions from the previous GATE papers and few questions on our own we discuss. Let us continue now the same Boolean algebra. What are the operators we discussed earlier? Those operators are this AND operator, OR operator, and NOT operator. These operators are named as basic operators. A part of these basic operators, we are having few more operators. They are NAND operator, NOR operator, exclusive OR operator, and exclusive NOR operator. All these operators are named as derived operators. These operators named as derived operators. Why we are naming these operators as a derived operators while discussing, it is possible to identify. Let us start with this NAND operator. NAND operator is basically this AND followed by NOT. So that we are having first AND operation, later we are having complement operation. All these operators what we listed here, they are similar to these AND and OR operators. All these operators are the binary operators, so that they are associated with minimum 2 operands. Suppose consider A and B are the Boolean variables. Then in the case of this NAND operation, first we are having AND operation on these variables. Later we are having complement operation. As a binary operator, in general, it may be on any number of operands. As similar to this AND and OR operators, here also on all these operators we need to look the truth tables on 2 variables and on 3 variables. We need to develop the truth tables on 2 variables and on 3 variables. While referring to the truth tables of the 2 variable and 3 variable, in general, as similar to this, possible to speak the result of the operation on any number of operands. So if we try the results on 2 variables, we need to list all possible combinations on these 2 variables. These are the possible values. These are the possible values on 2 variables. Similarly, while listing all possible combinations on 3 Boolean variables, these are the possible combinations on 3 Boolean variables. with the known result of AND operation, it is possible to look to the result of NAND operation. On two variables, when we are having AND operation, we know except the last row, for the remaining rows, result is 0. Except the last row, for the remaining rows, the result is 0. Whereas for the last row, the result is 1. When we are talking about this NAND operation, it is a complement of AND, so that except the last row, for the remaining rows, we are having as 1. For the last row, it is 0. So as similar to this, on three variable case, we are looking except the last row, for the remaining rows, the result is 1. For the last row, the result is 0. While looking to this two variable and three variable truth table, it is possible to speak about this NAND operation statement as the result of NAND operation is 0 if and only all the variables are 1. You can make a note. The result of NAND operation is 0 if and only all the variables are 1. If and only all the variables are 1. Or equivalently, alternatively, we can talk the result of NAND operation is 1 if at least one of the variable is 0. If at least one of the variable is 0. Whether we are looking to the two variable truth table or three variable truth table, other than the last row, guarantee for the remaining rows, at least one of the variable is 0. As and when one of the variable is 0, the result of the NAND operation is 1. From this two variable truth table, suppose if at all we are trying to look to the POS form for this NAND operation, we discuss how to write the POS form. To read the POS form from the truth table, we are referring to the combinations where the function output is 0. There's only one combination we are having function output is 0. So from this, possible to speak some term as A complement or with B complement, because A is 1, B is 1. Hence, it is possible to read here as A complement or B complement. Or you can say by using De Morgan's law, we are looking here, it is A complement or B complement. To perform this NAND operation, the logic gate is NAND gate. This NAND gate, symbolically we are representing with this symbol. This is the symbolic representation for this NAND gate. It is possible to look alternative gate for this while evaluating this expression by using De Morgan's property. Evaluating, we are having this expression is A complement or B complement or C complement and so on. While looking to this expression, it is possible to speak, it is nothing but a OR operation with inverted inputs. It is nothing but a OR gate with inverted inputs. A OR gate with inverted inputs must be named as bubbled OR gate. It must be named as bubbled OR gate. So based on this, we are looking a 9 is equivalent to a bubbled OR gate. or a bubbled OR gate is nothing but equivalent to a NAND gate. While discussing this AND and OR binary operators, I said whenever the logic gate is having more than one inputs, we are interested to look to the results such as if one of the input of the logic gate is 0, what is the output of the logic gate? If one of the input of the logic gate is 1, what is the output of the logic gate? If both the inputs, say A and B, both are connected to the same variable, say X, what is the output of the logic gate? And whenever both the variables are not connected to the same variable, what is the output of the logic gate? So we said this type of results we want to read on every logic gate whenever the logic gate is having more than one inputs. So let us try to look these results even for this NAND logic gate. If you look to these results, as I said, either using this truth table, either referring to this truth table or looking to the definition of the operation possible to speak these results. While looking at the truth table, if you see, whenever one of the input is 0, from this truth table you are looking, one of the input is 0 is the case for the first two rows. So whenever one of the input is 0, B may be of anything, the output is 1. So irrespective of the B, we are reading output is 1. In fact, there is a definition of the NAND operation. As and when at least when the input is 0, the result of the NAND operation is 1. And whenever one of the input is 1, A last two row में को refer कर रहा. In this case, we are looking. If B is 0, अगर B 0 रहे तो output 1, अगर B 1 रहे तो output is 0. So based on this B, we are having the result. We must speak this is complement on B. So it must be B complement. Hence, whenever one of the input is 0, for 2 input NAND, if at all we are looking, it is giving the operation as a not operation. Coming to the next case, whenever both the variables are connected to same Boolean variable X. So both the variables are connected to the same Boolean variable X is referring either maybe to first row or maybe to last row. First row, last row देख के बता सकते हैं अभी it is nothing but complement of the input. अगर input X 0 रहे तो output 1 है, अगर input X 1 रहे तो it is 0. So we are speaking whenever A and B both are connected to the same Boolean variable X, output is not operation, complement of the input. अगर inputs A and B same variable को connect नहीं हुआ, based on this condition guarantee, a condition के ऊपर guarantee है one of the variable will be 0. As and when one of the variable is 0, without looking to this table, we can speak output is 1. Or for clarity, if you want, you can refer to the middle two rows. There is a situation that is a case of A and B are not same. A part of this, इसके अलावा we said we are bothering to know this enable and disable inputs. We are interested to speak what is the enable and what is the disable input of this NAND operation. So enable, we said enable input will make the device used to be active, and the disable input we said the device will be inactive. So if you look here, enable input is possible as 1, disable input is possible as 0. It is possible to verify. Say for example, if we are having the NAND gate with 3 inputs, NAND gate, suppose we are having 3 inputs. अगर ये B 0 दिए तो A and C may be of anything. What we are reading? Output. Output क्या मिल रहा? Output is 1. So it means A and C variables we are not allowing to pass through this NAND. A and C variables are not passing through this NAND. A NAND gate से pass नहीं हो रहा. Such input is making the device is to be inactive. The such input is making the device is to be disabled. Based on this, a Boolean constant 0, we must speak it is the disable input. Similarly, अगर B variable 1 दिए तो while referring to the truth table, it is possible to speak the output will be AC complement. It means अगर B variable 1 रहे तो output is depending upon A and C values. It means A and C variables are allowed to pass through this gate. Such state of the logic gate we are speaking as enable state. Such input we are giving a name as the enable input. Hence, we are speaking enable input to this NAND gate is 1 and the disable input to this NAND gate is 0. Based on this, we are speaking enable input to the NAND gate is 1, the disable input to the NAND gate is 0. Let us come to the next operator. The next operator we mentioned in our list, that is a NOR operation. So NOR is nothing but OR followed by NOT. So that if A and B are the Boolean variables, we are having first OR operation, later we are having complement operation. So on these two variables, we are looking here A or B complement. As we said already, it is also a binary operator. So in general, on any number of operands, if you look, it must be A or B or C and so on, whole complement. We are having possibility to look to the result of this NOR operation from the known truth table of the OR. So from the known truth table of the OR, let us try here the results of this NOR operation on 2 variable case and on 3 variable case. Our result on 2 variable, except for the first row, for the remaining rows, the R result is 1. So based on this, the NOR result must be complement of this R. Hence, except to the first row, for the remaining rows, it is 0. Whereas for the first row, it is 1. So based on this, while coming to this 3 variable truth table, here also we are looking for the first row, it is 1, and for the remaining rows it must be 0. बाकी रो में 0 रहेगा, first row में 1 रहेगा. So while looking to this, definitely possible for us to speak as the result of NOR operation is 0 if at least one of the variable is 1. So you can make a note as the result of NOR operation is 0. The result of NOR operation is 0 if at least one of the variable is 1. The result of NOR operation is 0 if at least one of the variable is 1. So other than the first row, whether it's a case of the 2 variable or 3 variable, or for that matter, if at all we are trying to develop the truth table on 4 variable or 5 variable, other than the first row, for the remaining rows, guarantee we will be having one of the variable is 1. So that whenever at least one of the variable is 1, the result of the NOR operation is 0. Equivalently, it is possible to speak the result of the NOR operation is 1 if and only all the variables are zeros. All the variables will be 0, of course, only to the first row. All the variables will be 0 only to the first row, whether the case of 2 variable or 3 variable. Okay. Here also, the knowledge of SOP expression, if you try to look to the SOP expression on 2 variable NOR operation, to read the SOP expression, we must refer to the combinations where the function output is 1. Of course, it is the only one combination where we are having the function output is 1. As a product, if you read here, it must be A complement, B complement, because A is 0, B is 0. Hence, it is A complement, B complement. It is A complement, B complement. Or equivalently, we can talk by using the De Morgan's property. There is a 12th property what we listed. So by using De Morgan's property, it is A complement, B complement. The device which is performing this NOR operation is NOR gate. So this NOR gate, symbolically we are representing with this symbol. So similar to OR followed by this bubble. So you might understood by this time why we named these operators as the derived operators. We are looking in the definition of this 9, or in the definition of this NOR operation, we are having basically the usage of few of these basic operators. So while using few of these basic operators, we are having the definition maybe for NIND or maybe NOR. As similar to this, while looking to this XOR and XNOR later, we can recognize while looking to this XOR and XNOR operation also, we'll be having a conclusion, we'll be having the usage of few of those operators. Hence, as far as the basic operators are concerned, only these are the 3 operators which are the basic operators. All other operators, what we are discussing now, these operators must be named as derived operators. This NOR gate, here also we can look to the alternative symbol as similar to 9. For 9 alternative symbol, we were looking as bubbled OR gate. So based on this earlier knowledge, if we look here, it's supposed to be a bubbled AND, because while using the De Morgan's property, this expression we can read as A complement, B complement, C complement. So among these literals, we are having complement operation. Among these literals, we are having AND operation. So because of this, the gate is AND gate. We want to read this result here. So to read this result, the inputs what we are giving, they supposed to be inverted inputs. They must be inverted inputs. Then only the expected expression A complement, B complement, C complement we are reading. So this gate we must name as bubbled AND gate. This gate must be named as bubbled AND gate. So conclusion is a NOR gate is equivalent to a bubbled AND gate, or vice versa. A bubbled AND gate is equivalent to a NOR gate. Here also, if you look to these results, that is, while having one of the input is 0 and so and so, if you work out quickly based on our earlier knowledge, quickly we can speak now. Whenever one of the input is 0, whenever one of the input is 0, we are looking here. Whenever one of the input is 0, we are looking here. Looking to the table, you can speak, or directly also you can write with our earlier knowledge. It must be B bar, it must be 0. The reason is, whenever one of the input is 0, that is referring to the first 2 rows, a pehla 2 rows ko refer ho raha. So what we are looking, अगर b 0 रहे तो output 1 मिला, अगर b 1 रहे तो output 0 मिला. Hence इसके b we must write as a b complement. Whenever one of the variable is 1, then b may be of anything, we are reading output is 0, is 0 मिल रहा. So we are speaking, if we want to use a 2-input NOR gate as a NOT gate, as an inverter, then one of the input must be connected to 0. Whenever both the inputs are connected to the same Boolean variable, as usual, looking to the first row and last row, possible to speak it is complement of the input. So input is say x, then it is a complement of x. Looking to the first row and last row, we are able to speak. Whenever both the inputs are not connected to same Boolean variable, based on this condition, it is possible to look one of the variable guarantee as 1. Whenever one of the variable is guarantee as a 1, then output must be 0. And similarly, the enable and disable inputs you can recognize. If you quickly try with the for enable and disable inputs, you need to have a conclusion. Enable must be 0, disable must be 1. If you try on your own, you will be having quick conclusion based on our previous knowledge on AND, OR, and also the 9. Enable will be looking as 0. Disable input will be reading as 1. For clarity, we can verify. So let us consider it is a 3-input OR gate. So once it is a 3-input OR gate, the output expression is A or B or C whole complement. Suppose we are having B is 1. If B is 1, the other variables may be of anything. This is one complement effectively, so 0. It means we are looking here, this A and C variables are not getting chance to pass. Whenever A and C variables are not getting a chance to pass, such state of the logic gate we named as the disabled state or inactive state. So based on this, this input B equal to 1 must be named as a disabled input. Similarly, if B is 0, agar B 0 dihe to, what we are looking, we are having the output as A or 0 or with C whole complement. So iska meaning kya hai? A or C whole complement. It means A and C variables are It means A and C variables are getting chance to pass through this NOR. Such input must be named as enable input. Such state of the logic gate is an active state, so that such input must be named as enable input. Hence, enable input is 0, disable input is 1 for this NOR gate. Let us come to the next operator. The next operator is exclusive OR operator. This is symbolically represented with this symbol. I already mentioned all these are the binary operators. So minimum 2 operands are involving with this operator. A and B are binary operands. Then XOR operation among these operands, by using this symbol we are speaking as A exclusive or B or Y. We are writing as like this. As a binary operator, it may be on any number of operands. As usual, whenever we are having operator as a binary operator, we prefer to look to the result of the binary operator on 2 variables and on 3 variables. So let us try to look the exclusive result on 2 variables and on 3 variables. So on 2 variables, of course, we know these are the 4 possible combinations. On 3 variables, these are the 8 possible combinations. And we are having a result whenever only one of the variable is 1, whenever only one of the variable is 1, or all the 3 variables are 1, correspondingly, the result of exclusive or operation we are reading as 1. Whether it's the case of the 2 variable or 3 variable, we are having the result of the exclusive or operation as a 1, as and when only one of the variable is 1, only one of the variable is 1, or all the 3 variables are 1. Of course, for 3 variable case it is, the result is 1. All other cases, the result is 0. While looking to this 2 variable truth table and 3 variable truth table, definitely we need to speak the statement as, better note down, the statement must be the result of exclusive or operation, the result of exclusive or operation, the result of exclusive or operation is 1 whenever odd number of variables are 1. The result of exclusive or operation is 1 whenever odd number of variables are 1. Whenever odd number of variables are 1. So it is observation. The result of exclusive or operation is 1 whenever odd number of variables are 1. So based on this, the exclusive or operation is named as odd function. Based on this exclusive or operation will be naming as odd function. We are naming as odd function. Whenever odd number of variables are 1, correspondingly we are reading the result of XOR is 1. It's a reason to speak the exclusive or operation as odd function. From the 2 variable truth table, if we try for SOP form, the SOP form we are giving while looking to the middle 2 rows of the truth table. While looking to the middle 2 rows of the truth table, the one product is A complement B, other product is A B complement. So SOP form I said, so among these 2 products we are having OR operation, so that SOP expression for this 2 variable case is A complement B or with A B complement. If you are interested to write the POS form, then we must refer to the first and last row. So look at the first row, the sum term is A or B. Look in the last row, sum term is A complement B complement. So the POS form we are having as A or B and with A complement or B complement. So these are the SOP and POS forms respectively while looking to the 2 variable truth table. To perform this exclusive OR operation, the logic gate is exclusive OR gate. The exclusive OR gates are available with only 2 inputs. Practically, the exclusive OR gates are available with only 2 inputs. If we want the XOR operation on more than 2 variables, then we need to cascade. The exclusive OR gates. Cascading is nothing but one XOR gate output is coming as an input to the next XOR gate and so on. So the 2 input exclusive OR gate symbolically we are looking as like this. It is a symbolic representation for exclusive OR gate. As a question, if you look, why we must name it is exclusive OR gate? In the normal OR operation, for this 0 1 and 1 0, the result was 1. a part of this 1 1 was also inclusive. The normal operation, this 1 1 also inclusive. So for this 1 1, we were looking in the normal OR operation case, the result is 1. Whenever at least one of the variable is 1, the normal OR operation result is 1. So the normal OR operation, this was inclusive. So you can speak as an inclusive OR operation. Coming to this exclusive OR, this is exclusive. So this 1 1 is not used. Only 0 1 and 1 0 are, for this we are having result is 1. So it is exclusive. Based on this we are naming it as exclusive OR operation. If you look to these results, whenever one of the variable is 0, whenever one of the variable is 0, it is referring to, as usual, first two rows. So while looking at the first two rows, we are speaking it is same as the other input. Whenever one of the input is 1, looking to the next two rows, we are speaking it is a complement of other input. So whenever one of the input is 0, from the first two rows we are looking, if B0 output is 0, B1 output is 1, so it is a B. Whenever one of the input is 1, B if at all 0, it is 1, B if B is 1 means output is 0, it is a B complement. So we are looking here a speciality on this two input exclusive OR operation or this two input exclusive OR gate. We are having here one of the input with the name say M, other input let us name as X, and we are looking here the operation of this exclusive OR gate is dictated by this M. If M is 0, we are reading output is B. So whenever M is 0, the operation we are looking as the buffer operation. We are having this operation is a buffer operation. Buffer operation is nothing but sending input as T's to the output. That operation we suppose to name as buffer operation. And whenever M is 1, we are reading output is complement of the other input. When we are reading complement of the other input, it is a not operation, it is an inversion operation. So whenever M is 1, we are having the XOR operation is an inverter operation, not gate operation. So M is the one which is deciding or which is dictating the operation of this two input XOR. Based on this, the M we suppose to name as control input. M we supposed to give the name as the control input. It is controlling the operation of the two input exclusive OR. Whether to give the operation as a buffer or to give the operation as an inverter. It is controlling the operation. So it is a control input. See, if at all you are passing, somebody is stopping you, he is controlling you. As similar to that, whether to pass this X either as it is or the complementary form, it is controlling, it is stopping or it is controlling. Based on this, we suppose name it M as control input. It is one of the important usage of the exclusive OR gate. We are having the usage of the exclusive OR gate like this, many different practical circuits. I can quote a small example if at all you are remembering the binary subtractor circuit. When we are performing the binary subtraction operation, the hardware is adder circuit. With the help of the complement operation, we are performing subtraction. A plus B operation we are performing as A plus say 1's complement of B or A plus 2's complement of B. So whenever we are having such operation, we are having the usage of such exclusive OR gates. If you are remembering, okay, otherwise no need to bother. In the due course, as and when we are discussing the adder subtracts, we come across how we are using this exclusive OR gate there. Coming to this, whenever both the variables are connected to same Boolean variable, look into the first row and last row, we are speaking output is 0. Whenever both are not connected to same input, on two variable case only we are discussing, we are limiting our discussion on two variable case, it is 1. So whenever A and B both are connected to same Boolean variable, we are looking maybe to first row or maybe to last row, so it is 0. Whenever both are not connected to same input, look in the middle two rows, we are having the result is 1. And come to the next one, this enable and disable inputs. So try to think what is possible as an enable input and what is possible as a disable input. Try to think. So I was talking to identify the enable and disable inputs. Enable and disable inputs to this exclusive OR operation. If you identify properly, if you check properly, your answer on this question must be not possible to read any Boolean constant as a disable input, so that you can't read any Boolean constant as enable input. That is the conclusion you will be speaking. How it is so, we can verify while looking to the previous discussion. While looking at the previous discussion, possible to speak whether M is 0 or M is 1, we are reading output that is always depending upon the other input. Other input may be X or maybe B, whatever it may be. I think I was mentioning earlier X, but I think I given here it was B. So either way, it's not an issue. So whether it is B or X, we are looking here whether M is 0 or M is 1, we are reading output which is depending upon the other input B. It means whenever the other input is passing, then only we are able to speak the output. Based on this, we are not having any such input which is stopping the other input. As long as we are unable to identify any such input which is not allowing the other input or other inputs to pass, then based on this, you are having a conclusion. You can't read any Boolean constant as a disable input. Once we are unable to read any Boolean constant as a disable input, not possible to read any Boolean constant as enable input. Hence, for this exclusive OR operation, it is not possible to read any Boolean constant as enable or disable inputs. And one other point we can speak here, whenever A and B inputs are not same, whenever A and B inputs are not same, we are reading output is 1. Based on this, possible to speak the two input exclusive OR gate as inequality checking gate. Inequality checking gate. Suppose it is a two input exclusive OR gate. We are having A and B are the inputs. As long as we are having the output is 1, which is giving a meaning the binary values of A and B are not same. The binary values of A and B are not same means it is nothing but saying they are not same. Hence, we can speak now these two input XOR as inequality checking gate. So, the two input exclusive OR gate can be named as inequality checking gate. So, we can use the two input XOR gate to check whether two binary number values are same or not. Whenever the XOR result is 1, we are having a conclusion they are not same. Hence, we are speaking it is an inequality checking gate. From this 3 variable truth table, suppose we are interested to read compact canonical SOP forms and POS form. For that, of course, we must read equivalent decimal numbers. So, these are the equivalent decimal numbers. Now, the output Y as a function of 3 variables, compact canonical SOP form, they are having 1, 2, 4, 7. Compact canonical SOP form is 1, 2, 4, 7. So, you can speak now, we must name it is a odd function. We must speak this is a odd function on 3 variables. It is possible to speak it is an odd function on 3 variables. It was the question in 2009 DRDO exam. This question is available in the workbook chapter 2, question number 26, page number is 51. Page number is 51. So, question was, you can refer better while listening these video sessions, keep the workbook with you. It is always good. So, as and when I am referring to this, you can refer to the question directly while looking at that page. Question number 26, page number is 51. So we are naming on three variables. It was a question which one of the following function is odd function on three variables. So one of the option was 1, 2, 4, 7. I think it was option C. It was option C in the question paper. So option C, it is the right answer. So why we are naming the odd function? We already discussed while giving the truth tables itself. Whenever only one of the variable is 1 or all the three variables are 1, at that time we are having the result is 1. Based on this, I named in the beginning of this table itself, we are naming the OR operation as odd function. As similar to this, if you look to the POS form, the max terms, of course, the remaining combinations. The function is on three variables out of 8 combinations of three variables. 4 combinations we are reading as a min term. So remaining leftover combinations must be max terms. They must be 0, 3, 5 and 6. So we can have alternative representation for SOP and POS form in the compact canonical forms like this. Let us come to the next operator. The next operator is exclusive NOR operation. This exclusive NOR operation is nothing but XOR followed by NOT. XOR followed by NOT. Symbolically, we are representing this exclusive NOR operation with this symbol. It is a symbolic representation for exclusive NOR operation. So, if A and B are the Boolean variables, first on these variables we are having XOR operation, later there is a complement operation. Hence, the result Y we are speaking as A exclusive or B complement, or by using this symbol, it is A exclusive nor B. The exclusive NOR operation we are defining on only two variables. Exclusive NOR operation we are defining on only two variables. Why it is so, we'll speak later. So, while looking to the exclusive NOR result on two variables, possible to speak with a known truth table of this exclusive OR. With the known truth table of this exclusive OR, it is possible to speak. It must be complement of XOR. Once we are speaking complement of XOR, it is a truth table. So this will be A X NOR B. It is A X NOR B. So we are having exclusive NOR result is 0 whenever both the variables are not same. Exclusive NOR result we are having as 0 whenever both the variables are not same. Or exclusive NOR result is 1 whenever both the variables are 1. Here also, SOP form and POS form, if you try, the SOP form we are giving while looking at the first and last row. The first row product will be A complement, B complement. The last row product is AB, because first row A and B are 0, 0. For the last row, it is 1, 1, so that A complement, B complement are with AB. POS expression is A are with B complement and with A complement or B. POS expression is A or B complement and with A complement or B. The exclusive NOR gate symbolically represented with this symbol. And if you look to these results here, whenever one of the input is 0, we are speaking, it is giving the complement of second input. Whenever one of the input is giving is 1, it is giving the output same as the other input. As usual, looking to the first two rows and last two rows, we are speaking, whenever one of the input is 0, if B0 output 1, B1 output is 0. So we are speaking is a complement of other input. अगर एक इनपुट 1 है, बेस्ड ऑन द ट्रूथ टेबल, इसके ट्रूथ टेबल के हिसाब से बता सकते हैं, इफ B0 आउटपुट 0 मिल रहा, B1 रहे तो आउटपुट 1 मिल रहा. Hence B passing as it is a B. So possible to look here also. If I name one input is M, other input is X. If M is 0, we are looking output is a complement of the input. If M is 1, we are reading output is same as the input. So we are looking, this is the buffer operation. ये buffer operation है. This is inversion operation. It is the reverse to the exclusive OR. Hence, M is the input which is controlling the operation. So we are speaking M as the control input which is dictating the operation. Either maybe this, it is dictating the operation, this exclusive NOR, either maybe a inverter or maybe a buffer. So we are having inverter operation, NOT gate operation with this exclusive NOR gate whenever M is 0, and we are having the buffer operation with this exclusive NOR gate whenever M is 1. And coming to other two cases, whenever A and B both are connected to same Boolean variable, from the first and last row we are speaking it is 1. Whenever both are not connected to same input, look in the middle two rows, it is 0. And here also it is not possible to decide any Boolean constant as a disable input. Because we are looking here, whether M is 0 or M is 1, we are speaking the output which is depending upon the other input. Means irrespective of the M, we are looking here, as and when the X is passing, then only we are speaking what is the output. So X is allowed to pass whether M is 0 or 1. Based on this, you can't fix any Boolean constant as a disable. So the meaning of the disable we took, it will make the devices to be inactive. It is making the devices to be inactive means it is not allowing other variables to pass. It is not allowing other variables to pass. So it is not happening so whether M is 0 or M is 1, the other variable supposed to pass, then only we are speaking the output. So it is not stopping the other variable. As long as it is not stopping the other variable, it is possible to speak as we can't fix any Boolean constant as a disable input. As and when we are unable to fix any Boolean constant as a disable input, you can't fix any Boolean constant as a enable input. So we are unable to fix any Boolean constant disable, so we are unable to fix any Boolean constant as a enable. These are the results based on these conditions. And from this, again, you can speak about this exclusive NOR gate as whenever both the inputs are same, we are reading output is 1. Suppose it is exclusive NOR gate, whenever these are inputs A and B, whenever we are having result is 1, which is having a meaning A and B are the same values. If at all we are having A and B are some waveforms, whenever A and B waveforms are coincident, it is 1 to 1, point to point, A and B waveforms are same, then only we are having output is 1. Whenever A and B are coincident with the 1 to 1 from any duration of the time, for waveforms I am talking, if it is for any duration, we are having the point-wise same values, then only we are having exclusive NOR gate output is 1. Whenever they are having coincidence value, then only we are having output is 1. Based on this, we must name this exclusive NOR gate as coincident logic gate. We must name as this coincident logic gate. It must be named as coincident logic gate, or it can be named as equality checking gate. Equality checking gate. It can be named as equality checking gate. Related to this terminology, there is a question in the workbook. Related to this terminology, we are having a question in the workbook. The last year workbook it was there, it seems. Here, this year it is not there. But anyway, it is to be named as coincident logic gate. So finally, conclusion is whether we are having the NAND operation, NOR operation, exclusive OR operation, or exclusive NOR operation. In all these operations, we are having the usage of these basic operations. Based on this, these are the basic operators, and all other operators what we discuss, they must be named as derived operators. I was talking, we are limiting the definition of the exclusive NOR on two variable case. So let us discuss why it is so now. Suppose on these variables we are having exclusive NOR operation. On these variables, if we are having exclusive NOR operation, then to evaluate this, let us consider these together x, it is c, so that we are having here, this is x complement and c complement are with xc. So we are looking here a x nor b complement and with c complement are with a x nor b and with c. So alternatively we can speak this ax nor b whole bar, ax nor b whole bar is a exclusive or b. And this ax nor b possible to speak as a exclusive or b complement and with c. Just for our convenient, let me speak a exclusive or b, let us name as m. Then we are looking, this is MC bar or with M complement C. Then by using this terminology, we can rewrite this expression as MC complement or with M complement C. Hence, we must write this as M exclusive or C, where M is A exclusive or B, where M is A exclusive or B. Hence, we are looking, this is A exclusive or B exclusive or with C. Associativity is valid on exclusive OR operation. Once associativity is valid on exclusive OR operation, we are speaking here while removing the parenthesis, it must be A exclusive or B exclusive or C. We started here with the exclusive OR operation and we are reaching to exclusive OR operation. We started with the exclusive OR operation and reaching to exclusive OR operation. So it is a difficulty what we are having if you speak on more than two variables. If you speak XNOR operation on more than two variables, it's a difficulty with evaluation we are having problem. Hence, we need to speak now. Whenever we are having XNOR result on odd number of variables, whenever the result on the exclusive NOR on odd number of variables, when we are having XNOR operation on odd number of variables, the result of XNOR and XOR is same. The result of exclusive NOR and exclusive OR is same. It is a case whenever the operation is odd number of variables. So the discussion what we had, which was on 3 variables, it is a case of odd number of variables. So whenever we are looking to the XNOR result on odd number of variables, the result is coming to be same as exclusive OR. But whenever this exclusive NOR operation we are looking on even number of variables, we are having a conclusion the XNOR result is coming as complement of exclusive OR, is resulting complement of exclusive NOR. It is a case, the 2 variables. 2 is the case as even. So whenever we are having exclusive NOR operation on even number of variables, that is 2 variables, 4 variables, etc., the XNOR result is complement of XOR, so that XOR, XNOR are complement to each other on even number of variables. But on odd number of variables, XNOR result and XOR result is same. So it's the one what you need to remember well. This is the one what you need to remember well. On even number of variables, XNOR, XOR result is complement to each other. On odd number of variables, XNOR and XOR results are same. As I was talking, if at all we want the XOR operation on more than 2 variables, say if you want to have the exclusive OR operation on 3 variables, if you want exclusive OR operation on 3 variables, then it required for us to use 2 exclusive OR gates. The first exclusive OR gate is having the inputs, this A and B. The second exclusive OR gate is having one of the input, this is gate 1 output. Second exclusive OR gate, one of the input is the gate 1 output, and second input is C. Then we are looking to the Y as A exclusive or B exclusive or C. In fact, it can be read as A exclusive or B parenthesis exclusive or C. But associativity is valid on exclusive OR operation, so it is A exclusive or B exclusive or C. Hence, if you want XOR operation on more than 2 variables, like this will be connecting. This sort of connection we are naming, in fact I use that word, we are naming as cascading connection. So one output of one of the gate is coming as the input of the next gate, that is to be named as a cascading connection. So if you want XOR operation on more than 2 variables, it is a way we need to work. It is a procedure we need to follow. This associativity property. The associativity property is valid on AND operation, on OR operation, and on exclusive OR operation. It is valid. But on NAND operation and NOR operation, associativity property is not valid. Associativity is not valid. We can verify how it is so. Suppose with the AND, if you want to verify on three variables, we are having AND operation as A, B, and C. The logic gates we are checking, then we are looking here. It is AB. The gate 1 output is one of the input of the gate 2. Gate 2 second input is C. So the truth table, if you verify, this will be coming to be ABC results. Hence, associativity is valid on AND. The same similar verification you can do on OR. On XOR also said, I given a circuit also there. So if you check like this with the cascade connections with the truth table, you will be having a same truth table, same results, so that we are having the validity of associativity on AND, OR, and exclusive OR operation. But if you look to this NAND and NOR, associativity is not valid. Suppose on these ABC variables we are having NAND operation. So this NAND result we are having on ABC, of course, by using 3 input NAND gate. If you try for this result with the 2 input NAND gates, the gate 1 output is AB complement, gate 2 input is AB complement, second input is C. Hence, we are having the output suppose if I name it is F. F is AB complement AND with C whole complement. Evaluate this by using Demarcan's property. We are having effectively this will be AB or with C complement. AB or with C complement. So AB complement and one input to the second NAND gate, second input is C, so AB complement AND with C whole complement. Hence it is AB or with C complement. The conclusion is this F is not equal to Y. Once this is not equal to Y, this is not equal to this result, we are having a conclusion associativity is not valid on NAND operation. The same thing if you try with an OR, you will be having a conclusion the associativity is not valid even for NOR operation. Whereas it is not the case with the AND, OR or XOR. So for AND, 3 input gate inputs, if at all ABC, we are having it is ABC. If I name, suppose as similar to that, if I want to stock, if I name it is F, F is coming to be equal to Y. So it is one and same. But here it is not the case with the NAND or NOR. So associativity is valid on AND, OR and XOR. Associativity is not valid. Is not valid on NAND and NOR. Let's try now few problems which are on exclusive OR and exclusive NOR. Note down. Simplify the given Boolean equations. Simplify the given Boolean equations. First question is y is equal to a exclusive or with a b complement exclusive or with a complement. Second one, f is equal to a exclusive or b exclusive or with a exclusive or b complement. So if you look to the solution to the first question, if it is a multiple choice, then without doing any sort of work, we are having possibility to pick the answer to this question. If it's a multiple choice question, where the option must be this A complement or B. So from the options, we are having possibility to pick this as answer without any paperwork. So it is an expected practice. So how we are giving this as answer, if you see, associativity is valid on exclusive or operation. So A exclusive or A bar possible to read first because associativity is valid. A exclusive or A bar result is known for us. For that, we are having a listed information while discussing the truth tables. So whatever things we learn, we need to use. We listed those things to use effectively, not just noting in the notebook and forgetting is not the case. So to use the things what we learned, that is the purpose. Hence, A exclusive or A complement is 1. So we are looking here 1 exclusive or with A B complement. It is also available in our work, in our previous work. Whenever one of the input of the exclusive OR is 1, XOR output is a complement of the other input. So based on this, this will be A, B complement, whole complement by using, definitely the answer in the options is not like this. By using De Morgan's property, we are having this result is this A complement or B. Hence, the answer to the first question is A complement or B. And coming to the next question, hopefully you might be answered by this time. By this time, you might be thought of the answer. The answer to this question must be 1. And if you look how it is so, associativity is valid on exclusive or operation. So based on this, we are reading here A exclusive or A. Whenever A exclusive or A, we are reading from our known results which are listed while discussing the truth tables of XOR. A exclusive or A is 0. Whenever A and B are connected to same variable, it is 0. And B exclusive or B bar, that is 1. So effectively, it is coming 0 exclusive or with 1. Will be 1. Will be 1. So such type of practice is expected. Okay, one of the approach we followed and we are having from this approach, the A exclusive or B, exclusive or with A exclusive or B bar as 1. If we are having doubt how far it is right, if that is a question we want to speak, we want to take. If we are having a question like this, and with the known answer, with this known answer of 1, if at all we are looking, the answer 1 is possible to be true. The answer 1 is possible to be true if and only among these two terms we are having a relation as something X exclusive or X complement. The answer what we are speaking as a 1 is possible if and only among those two terms, if at all the relation is looking as exclusive or between X and X bar, then only it is possible. So let us verify such a relation is existing among these two terms or not. As it is on A exclusive or B, there is no scope of doing any work possibility. So To justify this, the possibility we are having, to justify this, the possibility if you try, the possibility is supposed to be this A exclusive or B supposed to be A exclusive or B complement. In other way, it must be equal to A X nor B. Then only the answer what we are speaking must be correct. Let us verify whether such a result we are having or not. Just for our convenience to evaluate this, let us name it is X. So X we are taking as B complement. Based on this, X complement is B. While evaluating this A exclusive or X, we are looking here A complement X or with A X complement. A complement X, X is B complement. X is B complement. X complement is B. As we are very much aware, this is A X nor B. So conclusion is A exclusive or B bar is equal to A X nor B. Once A exclusive or B bar is equal to A X nor B, what we were expecting, such a relation is existing among these two terms. Hence, the answer what we mentioned is right. So while practicing the questions, we supposed to think like this. If you think like this, default we are learning some new things. Whenever we are learning new things on our own, generally we may not forget that easily. And basically it will motivate us to learn the subject. It will motivate us to do more problems. So whenever we are practicing questions like this, not only in this subject, many subjects it is possible to work like this. Wherever it is possible, we need to think like this. We'll be having a self-motivation. With that, we'll be getting interest to read the subject. We'll be getting interest to refer to different textbooks or questions, etc. So like this, we need to think. So while working on this problem, while thinking like this, we are default learning a new relation. The new relation what we are looking is A exclusive or B bar is equal to A X nor B. Such a new relation we are able to understand, we are able to identify. Let's try. Next problem. In the given logic circuit, 20 exclusive OR gates. In the given logic circuit, 20 exclusive OR gates are connected as shown below. Are connected as shown below. In the given logic circuit, 20 exclusive OR gates are connected as shown below. Identify the output. Identify the output Y. Identify the output Y. In fact, it is the question in the workbook. Try yourself. First question T1. Page number is 52. Page number is 52. fact, it is a GATE question in the 2002 GATE exam. It was a question. It was a question EC paper. Of course, few of the questions what we are discussing in the class, they are from CS GATE paper. Few questions may be from EC, few may be from instrumentation, or few may be from the electrical GATE papers, or sometimes maybe few questions from engineering service papers also. Of course, as I said in the introduction part, the syllabus of this subject, major syllabus, major portion is same among many branches for CS, EC, EE, instrumentation. Anyway, hopefully you might try it by this time. The answer you might be identified. The answer to this question must be 1. The question what we are looking is the 20 exclusive OR gates are connected, are cascaded as shown below. It is a question. So if you look here, the first gate, one input is 1, other input is A. We are already having the known knowledge on XOR operation. Whenever one of the input is 1, the XOR is giving the complement operation, not operation. Hence, the first gate output is A complement. So, second gate inputs, we are looking, one input is A complement, other input is A. Whenever both the inputs are not same, that is also known for us, that is 1. If you think like this, after third gate, we are having, it is A complement. Because for third gate is concerned, one of the input will be 1, the next input is A, second input is A. So, third is coming to be similar to the gate 3. And fourth is coming, one input is A complement, other input is A. So, similar to this second gate. If you think like this, after even number of exclusive OR gates, we are having the result is 1. Hence, answer to this question is 1. Instead of even number of gates, the same question if you consider an odd number of logic gates, then definitely our answer will be A complement. Instead of even number of exclusive OR gates, if at all we are having odd number of exclusive OR gates, maybe say 19, 17 or 5 or 8, 5 or 7 or something 13, etc. Whenever we are having odd number of gates, the result will be A complement. Whenever even number of gates, the result will be 1. Let us come to the next question. Next question is, note down, the variable A is having XOR operation itself. The variable A is having XOR operation itself n number of times. The variable A is having XOR operation itself, XOR operation itself n number of times. N number of times in the above equation. The variable A is having XOR operation itself n number of times in the above equation. Then, first case, if n is even, if n is even, what is the output y? Second case, if n is odd, if n is odd, then what is the output y? Then what is the output y? You can think and you can try. The question what we are looking is, there is a Boolean expression y. The y expression is given as a exclusive or a, and so on. The question what we are looking is, the variable a is having XOR operation itself. The variable a is having XOR operation itself n number of times. Then, if at all n is even, what is the output y? If n is odd, what is the output y? Is the question. Is a good question, interesting question. It was this similar type of question was the question in the GATE paper sometime back 98 in the GATE paper. And similar question I mentioned even in the workbook. I will give the question number later. We'll speak the question number of workbook later. There's a question in the second chapter in the workbook. Similar thing. So, if you look here, suppose I'm having A exclusive or A exclusive or A. Tell me, what is the n value? And similarly, A exclusive or A exclusive or A exclusive or A exclusive or A. What is the n value? Similarly, A exclusive or A. What is the n value? A exclusive or A exclusive or A exclusive or A. What is the n value? Based on the question, if you look here, n is 2. Here n is 4. Whereas here n is 1. Whereas here n is 3. Hence, we are looking based on the question, it is a case of even and it is a case of odd. So what we are looking, the statement of the question, the variable a is having XOR operation itself n number of times. The variable a is having XOR operation itself n number of times. Whenever n is even, he is talking. Whenever n is even is the case in this 2 times, the operator is repeating. So it is even. Here it is repeating, operator is repeating 4 times. So it is a n is 4. And similarly coming to this, operator present only single time, so 1. Operator present 3 times, so it is 3. So the statement what we are looking here, this statement if you look well, the statement is not on the repetition of the variable a. The statement is not on the repetition of the variable a. The statement what we are looking is repetition on the operator. So it is related with the operator. Be careful. So whenever we are having questions of this nature, always good to read the statement more than once. When in the exam hall, I am suggesting. Small wording will make a difference to speak the right answer. So variable a is having XOR operation itself n number of times. Here, variable a is having XOR operation how many times? We are looking here. It is having XOR operation itself 2 times. Here, 4 times and so on. So it's a means here to understand. So with this proper understanding the statement, if you come to the question, definitely you will be giving right answer. But without understanding or without keeping proper attention while reading the statement, if you are trying to look to the solution, there is a possibility you may do the mistake, you may pick the wrong answer. Mostly it may be a multiple choice question, so you may pick to the wrong answer. So keeping attention is very important. So anyway, if you look here, Associativity is valid on exclusive OR operation. A exclusive OR A we can read first. It is 0. Then 0 exclusive OR A. All these are available while discussing the truth tables we discuss. It is A. And similarly here A exclusive OR A we can read. Here A exclusive OR A we can read. It is 0. It is 0. 0 exclusive OR 0 is 0. Finally 0 exclusive OR A is A. Coming to this, A exclusive OR A, it is 0. Coming to this here 0, this is 0. 0 exclusive OR 0 is 0. So, what the conclusion we are looking? Whenever n is even, we are having output y as equal to A. Whenever n is even, we are reading output as equal to A. And whenever n is odd, we are reading output as equal to 0. Whenever n is odd, we are reading output as equal to 0. So answer to this question for first case, whenever n is even, we are looking to the answer as A. And whenever n is odd, we are reading the answer is 0. Okay. I will modify this question now a little. The question I am modifying here, say, let me name as a fifth question. I am taking here the statement as the variable A is present A is present n number of times in the above equation. Fifth question I said the variable A is present n number of times in the above equation. Then if n is even, what is the output y? If n is odd, what is the output y is the question. It was as it is the solution for fourth question. The same work, if at all we want to use, even the solution to the fifth question, we are looking here. Here, n values if read based on the statement, n values if read, variable A is present here 3 times. So, n is 3. Variable A is present here 5 times. It is 5. The question what we are looking is, the variable A is present n number of times in the above equation. So, here variable A is present 3 times. Here variable A is present 5 times. Similarly, coming to this, here variable A is present 2 times. Here variable A is present 4 times. Based on the question description, now this is the case for odd. It is the case for odd. If n is 3 or 5, it is a case for odd. And when n is 2 or n is 4, it is a case for even based on the question. The variable A is present in the above equation n number of times. So, whenever n is even, we are referring to this. Whenever n is even, that is 2 or 4 times, we are having output is 0. We are having now output is 0 for this fifth question. And whenever n is odd, we are having output is A. We are reading output is A. So, these are the answers on the fifth question. Hence, as I was talking, whenever we are having some statement like this, as and when for on any question we are having little lengthy description to speak the answer before coming to the conclusion to the answer, better to read the question better more than once. So the wording what we are looking in the statement, that matters very much to identify the proper answer. Question may not be complex, but understanding question is important. Understanding question you can do well if you are having with proper attention if you read the question. So without any tension, if at all you are sitting in the hall, that make you sense to avoid all these things. So without tense, you will be sitting the class in the hall, exam hall, or exam time you will be having without tension. If at all you are having proper sleep before the exam day. So with overnight reading, if at all you are going to exam hall, all inbuilt problems, biological problems will be there. So definitely it is a little difficult keeping attention. You will be having little sleepy mode, and sometimes the beginning itself we are looking one or two questions which are looking to be very tough. Then your mood will be off. All this will make you to not to perform well, even with your good preparation. It may give sometimes a wrong result or may not be giving expected good result. Okay. As I was mentioning, a similar question is available in the workbook. I will tell you which is that question. Question number I will speak. It is in the second chapter. A similar question you try. It is more or less same. Question 14 in page number 49, as I've said, it was similar question in the 98 gate CS paper itself. It was a question. So what are the things we discuss while watching till now? What are the things you learned while watching the videos till now? What are the things you learned? With those learnings, try yourself the questions from the workbook of the chapter 2. Hopefully, you can do on your own many questions. You can do many questions on your own. So anyway, in the due course, I will be giving the key or maybe on few typical questions, complete solutions I will be providing. But in the meantime, before waiting to my turn, if you try yourself, it is better for you and you will be getting interest. You will be having some feel you are able to do problems. And many questions what you are looking in the workbook, they are from previous GATE or previous engineering service, or maybe some questions ISRO or DRDO question papers. And of course, few questions I designed on my own. So all are very good, and you will be having proper sequence also in the what way we are discussing the subject sequence in the class. More or less, the sequence, same sequence is I mentioned in the same sequence questions I mentioned in the workbook also.